Imagine having the entire planet's weather and climate data, not just sitting on these massive servers, but kind of distilled into just a few gigabytes.
Yeah, ready for you to explore interactively, instantly,
Exactly. Like, what if you could ask those what-if questions about climate change?
and get back really high-resolution, scientifically solid answers?
Mm-hmm.
Well, almost immediately.
It sounds a bit like science fiction, honestly.
It really does, but that vision, that's pretty much what we're going to unpack today. It's a potentially huge shift in how we deal with climate information.
It really is. So today we're doing a deep dive into climate in a bottle, or cBottle.
Right, this new generative AI framework from NVIDIA researchers.
Our mission really is to explore how this tech is changing our ability to, understand and interact with these huge climate data sets. Petabyte scale, we're talking.
And offer you, the listener, maybe a shortcut to getting your head around one of the most complex topics out there.
So cBottle at its heart, it's designed to emulate climate simulations, right? Global kilometer scale stuff.
That's the idea. Emulate those simulations and also reanalysis data. Think of it like, literally putting the whole global atmosphere into a tiny, accessible bottle.
The main goal being low latency access, interactivity.
Precisely. Making these super detailed global climate projections, but with local detail, available basically on demand to, well, potentially anyone.
Which sounds amazing because anyone who's wrestled with climate data knows the current way. It's just a colossal effort, isn't it?
Oh, absolutely. It's a massive bottleneck.
What are the biggest headaches cBottle tries to fix?
Well, you've got climate science generating petabytes, just enormous amounts of this kilometer-scale data from supercomputers, from satellites.
Okay.
But actually getting to that data, interacting with it, that's the hard part. It's often stuck in a few big climate centers.
Right, so accessing it takes forever. High latency.
Exactly. Retrieval can take days, sometimes weeks. Just moving that much data around is incredibly slow.
Even with projects like Destination Earth or EVE.
Yeah, those digital twin initiatives, they envision this accessible, interactive future.
Yeah.
But the current methods, the way we store and move data, they really struggle to make that vision practical.
It's like having this giant library, but fetching one page takes a week.
That's a good analogy, yeah.
Yeah.
So AI comes in. How does it break that bottleneck? Generative AI specifically.
Well, these AI emulators, they offer a path that's just orders of magnitude faster.
Orders of magnitude, wow.
Yeah. Better computational performance, and this is key, often improved accuracy compared to just running traditional simulations over and over.
So instead of running the complex physics simulation every time.
You're asking an AI model that's already learned the patterns, learned the physics, essentially.
And when we say AI here, we're talking about a foundation model. We should probably define that for climate, shouldn't we? Why is that term important?
Good point. So for this deep dive, let's define a generative foundation model in the climate context as a self-supervised climate simulator.
Self-supervised, meaning it learns from the data itself, without explicit labels for everything.
Exactly. It figures out the patterns in these vast data sets on its own. And crucially, it needs to produce realistic samples. Climate faithful is the term they use.
Samples you can use for those what-if scenarios.
Yes.
Even ones it wasn't explicitly trained on.
Right. Now, physics-based models, general circulation models, they've done similar things for ages.
Sure, GCMs are the bedrock.
But the difference here is the ease of use, the performance boost from AI. It's really shaking things up. It's moving from pre-calculated scenarios to something much more flexible, on-demand insights.
Okay, so that's the foundation model idea. Now, how does cBottle actually work? I know many AI climate models predict step-by-step through time. Autoregressive, right?
Yeah, that's a common way, but cBottle does something different, which sounds quite innovative.
It does. It uses a generative diffusion-based framework. Instead of stepping forward in time, it learns the whole distribution of possible climate states.
Learns the distribution.
Okay. And then it samples from that distribution.
Yeah.
This is really good for doing rapid analyses.
And it has another advantage over the autoregressive ones.
Yes, it seems less prone to instabilities or drifts. Sometimes people call them AI hallucinations, where the model just veers off into unrealistic territory over long simulations. Diffusion models seem inherently more stable.
Okay, so it samples states, and it does this in a two-stage process, a cascade.
Exactly, a two-stage cascade. It starts with stage one, the coarse-resolution generator. They call it cBottle 3D or cBottle video.
Coarse-resolution. So the big picture first.
Right. This first stage generates fields at 100-kilometer resolution. Think of it as around 50,000 pixels covering the globe, a lower detail snapshot.
And the inputs required are surprisingly minimal.
That's one of the most striking things. It's conditioned on just monthly average sea surface temperatures, SSTs, and basic solar conditioning. Time of day, time of year, that's it.
Just that. For global atmospheric fields, that seems incredibly efficient.
It really is. And another key innovation is how it handles different types of data. Multimodality data bridging.
What does that mean in practice?
It means it combines data from observations, specifically the ECMWF reanalysis version 5, ERA5, and data from a free-running climate model, the ICON model.
So it learns from both real-world observations and simulation data.
Yes. It leverages the strengths of both. It's like teaching someone using both real examples and theoretical explanations. You get a richer understanding.
And the data efficiency, I read it can be trained on just 4 weeks of simulation output. That's tiny.
It's remarkable data efficiency.
Yeah.
And on top of that, the compression is extreme.
Right. You mentioned putting the atmosphere in a bottle.
It encapsulates these huge kilometer-scale model outputs and reanalysis data into just a few gigabytes of neural network weights.
Few gigabytes? From petabyte?
Yeah, they quote a 256x compression ratio per channel. Think about it. You go from needing like a whole data center's worth of storage.
To maybe a single USB drive?
Effectively, yes. A drive that can then generate the data you need when you need it. That's what could democratize access.
Okay, wow. But climate data lives on a sphere. That's always tricky for computer models, right? How does cBottle handle the globe?
Good question. It uses something called the HEALPIX grid. HEALPIX.
HEALPIX.
It's a smart way to divide up the sphere into equal area pixels or grid cells. Very handy for deep learning.
Equal area, so no distortion near the poles like you get with simple maps.
Exactly. Crucial for accurate global modeling. And they use special ways to handle the edges of this grid when they process it, padding protocols, to make sure calculations flow smoothly across the whole globe. No weird seams.
Okay, makes sense. Now, there was this fascinating detail about the noise schedule used during training. Why is that so critical here?
Ah, yes, the noise schedule. It's more important here than, say, typical image generation.
Why is that?
Because climate data has these incredibly strong, predictable patterns on a planetary scale. The seasons, the day-night cycle, they dominate the signal. So if you don't add enough randomness, enough noise during training, the model might just latch onto those obvious cycles. It sort of cheats.
It doesn't learn the underlying physics, just the big patterns.
Right. They mentioned an example where it produced a double sun artifact because it was picking up residual signals instead of truly learning from the time of day input.
Yikes. So how does cBottle avoid that?
It uses a specific log uniform noise schedule, and crucially, with a much wider range of noise levels than usual, from very low noise to very high noise.
A wider range. Why does that help?
It effectively masks those big dominant signals, the seasonal cycle, the diurnal cycle. It forces the model to dig deeper and actually learn the physical connections, like how solar input drives atmospheric changes, rather than just memorizing the average patterns.
So it has to learn the real dynamics.
Yeah.
Got it. And then there's an extension, cBottle video, for temporal coherence.
Yeah, that adds time into the mix for this first stage. It uses temporal attention layers.
Letting it generate sequences, not just snapshots.
Exactly. It can generate 3-day sequences with 6-hour resolution. So you see the atmosphere evolving realistically through time, like a short movie clip instead of just a photo.
Okay, so stage 1 gives us this coarse resolution dynamic picture. How do we get the really fine-grained detail needed for local impacts? That's stage 2, right? The super resolution module.
Precisely. cBottle SR. This takes the 100-kilometer outputs from stage 1.
And zooms in.
You could say that. It's locally trained to perform a 16x super resolution. That bumps the detail up to 5-kilometer fields.
5 kilometers is getting really detailed. How many pixels globally?
About 12.5 million pixels. Now we're talking much more actionable resolution.
But doing super resolution globally must be computationally intensive.
Very. So they use a clever trick. Overlapping patch-based multi-diffusion.
Patches?
Yeah. They break the global map into smaller overlapping squares or patches. They apply the super resolution process to each patch individually.
And then stitch them back together.
Right. The overlap is important. It helps minimize any weird artifacts or edges where the patches meet, makes it seamless.
In this super resolution stage, it's not just about making sharper images, is it? You mentioned it has capabilities beyond just emulating the data.
Absolutely. This is where things get really exciting and point towards that foundation model idea. This cBottle SR module shows real promise for tasks like, well, zero-shot bias corrections.
Zero shot, meaning it can do it without specific training for that task?
Kind of. Also, climate downscaling and channel infilling. These are powerful tools for climate science, going beyond just replicating data to actually improving it or adapting it.
Okay, incredible potential.
Yeah.
But how do we actually trust the data coming out of cBottle? How do we know it's climate faithful, as they say?
That's obviously critical. They tested it rigorously using what they call a battery of climate model
A
diagnostics.
battery,
Yeah.
like a whole series of tests.
Yeah, standard tough tests used in the climate modeling community to check if a model realistically captures the Earth's climate system. Not just the averages, but the variability, the extremes, the complex behaviors.
Okay, let's dig into those results. First, the ERA5 in a bottle part, the coarse-resolution emulation. Did it get the basics right, like seasons, precipitation patterns?
It did. The paper shows it correctly generates the seasonal changes in Arctic sea ice, for instance.
Okay, that's fun about.
And it produces realistic patterns of annual mean precipitation. Matches the ground truth from ERA5 pretty well. So yes, the basic climatology and seasonal cycles seem well captured.
What about more complex things? Tropical cyclones are notoriously hard to model.
That's a big test, definitely. And cBottle did generate tropical cyclones in the right places, like the tropical basins where they occur.
And with the right frequency.
Yes, with accurate occurrence probabilities. That suggests it's capturing realistic synoptic variability, the day-to-day weather patterns that spawn these storms.
Impressive. What about really subtle things, like the daily cycle of rainfall?
It even reproduces details of the diurnal cycle, including subtle spatial patterns over tropical continents.
Like what?
Well, they mentioned this halo effect around the maritime continent, Southeast Asia, Indonesia, that comes from how convection tends to be phased through the day. cBottle picked that up.
Wow, that's a very specific, nuanced detail.
It is. It shows it's not just getting the broad strokes.
Okay, let's go bigger scale.
Yeah.
Planetary modes, like the northern annular mode, the NAM, these big oscillating patterns.
Yes, it captures the main pattern of the NAM, what scientists call the leading EOF, or empirical orthogonal function.
The dominant mode of variability.
Essentially, yes. It captures how pressure patterns over the Arctic shift and influence weather across the hemisphere, and it shows realistic day-to-day variability in this mode, linked to the sea surface temperature input it receives.
And ENSO, El Niño and La Niña, that has huge global impacts.
Because it's conditioned on those sea surface temperatures, it does produce realistic precipitation changes associated with ENSO.
Like more rain in the Central Pacific during El Niño?
Exactly. And less rain over places like Indonesia, tropical Africa, South America. Patterns consistent with how the Walker circulation changes during ENSOA. So it links ocean conditions to atmospheric response correctly.
What about extremes, like heat waves? Especially trends in extremes, which is obviously a huge concern.
This was interesting. The paper notes it struggles a bit with capturing the overall surface temperature trends correctly.
Okay. A limitation.
But it can reproduce observed trends in measures related to extreme heat. Specifically, the frequency of high geopotential heights at the 500 HPA level.
Which often correspond to heat waves.
Yes, those strong, high-pressure systems. It generated trends in those extreme height occurrences that were quite similar to observations, especially over land.
So it captures the atmospheric setup for heat extremes, even if the surface temperature trend isn't perfect yet?
Seems that way, yes.
All right, let's switch to the icon in a bottle results. This involves the super resolution and the full end-to-end generation. How does that super resolution look? Does it feel realistic?
Qualitatively, the researchers say yes. It generates fine details, like the structure within tropical cyclones, eye walls, rain bands.
Things that weren't in the coarse input.
Exactly. Plausible-looking frontal systems, too. Features that emerge from the super resolution process.
And quantitatively, do the stats back it up?
They looked at spherical power spectra. It's a way to measure how much variance or energy there is at different spatial scales.
Okay.
And the spectra from cBottle's super resolves output matched the ground truth icon data well. So it has the right statistical texture across scales, not just pretty pictures.
Good. Now the end-to-end generation. Making those 12 million pixel icon states just from noise and the basic conditioning. How well does it handle multiple variables at once?
They found encouraging co-generation, meaning it generates variables like, say, outgoing radiation and precipitation together in a physically plausible way.
So the clouds and rain make sense together.
Yes, you see realistic, multi-scale associations. Fine-scale rain embedded within larger cloud patterns near the equator, for example. Things that look right to a meteorologist's eye. And spectral analysis confirms this consistency across variables, too.
And the video aspect, the cBottle video, does it show weather systems moving realistically over time?
Yes, they tested that specifically with mid-latitude storm tracks. The video model reproduced the way these storms evolve and move eastward,
At the right speed.
at comparable speeds to the ground truth icon simulation. This is important. It suggests the model is capturing the underlying physical dynamics of the atmosphere, not just it generating a sequence of plausible but disconnected states. It understands flow.
And that data efficiency you mentioned for the coarse model, did that apply to the super resolution 2 training on just 4 weeks?
They did an ablation study, basically, testing different training setups. And yes, training the super resolution module on just 4 weeks of icon data, carefully chosen to cover different seasons, gave results in terms of spectral characteristics that were nearly identical to training on almost 4 years of data.
4 weeks versus 4 years. That's astounding efficiency.
It really highlights how effectively these models can learn, which is a massive advantage, especially if you don't have infinite computing resources.
Okay, so this brings us back to the idea of going beyond emulation, where cBottle acts like a true foundation model.
Exactly. Leveraging what it learned across different data sets and tasks, this is where the versatility really kicks in.
You mentioned icon-informed downscaling of ERA5. How does that work? It learned on icon model data, but improves ERA5 observational data.
Right. This is a zero-shot generalization.
Yep.
The super resolution part, cBottle SR, was trained only on the icon simulation data, but they fed it the coarse ERA5 observational data. And the fine-scale details it generated looked more like native icon data or even high-resolution weather model data like HRRR than the original blurry ERA5.
So it's adding realistic detail learned from the simulation to the observations.
Precisely. It's transferring knowledge from one domain simulation to another observation without explicit training on that specific transfer task, enhancing real-world data.
That's powerful. And channel infilling, what problem does that solve?
Sometimes data sets have missing variables or corrupted data in certain channels. ERA5, for example, has some issues with its radiation channels.
Okay.
cBottle, having learned the relationships between variables from the complete icon data, could actually reconstruct those missing radiation channels in ERA5.
Wow, fill in the gaps.
Yes. And it even removed known visual artifacts streaking that were present in the original ERA5 radiation data. It used its icon knowledge to clean up the ERA5 data.
That's like data recovery using AI.
Essentially, yes. A very powerful tool for improving existing data sets.
This really does sound like a foundation model, learning across sources, applying knowledge flexibly.
It points that way. And the final example is bias correction.
Adjusting one data set to match another?
Exactly. They showed it could take the icon model output and adjust its cloud properties, specifically the balance between liquid water and ice in clouds, to better match the typical characteristics seen in ERA5.
So translating between the dialects of different data sets.
That's a great way to put it. Using the shared understanding it built during training the latent space to harmonize them. And it did this while keeping the changes consistent over time in the video sequences.
That ability to translate, that really feels like a hallmark of these foundational models.
It is. It suggests potential for making different climate datasets more comparable, more useful together.
Okay, let's try and wrap this up. We've explored climate in a bottle. This technology offers just unprecedented compression. What was it, 3,000x per sample?
Something like that overall, yeah. And low latency generation of data, plus this amazing versatility.
It really seems like a leap forward in tackling those bottlenecks we talked about. Storage, data movement, I/O in climate science.
Definitely. Instead of waiting days or weeks to retrieve stored data, cBottle allows you to generate realistic kilometer-scale climate data almost instantly, on demand.
From a compact model.
From a compact machine learning model, it fundamentally changes how you might access and use climate information.
So this deep dive, it's shown us the outlines, maybe the beginnings, of a true climate foundation model.
One that learns from different sources, observations, simulations, and transfers that knowledge. A kind of intelligent hub for climate data.
And these abilities, cross-modal learning, infilling, bias correction, they seem incredibly useful.
They can be huge for climate science itself, but also for how society uses climate information for decision-making, making data more robust, more accessible, more tailored.
So thinking about this, what does it mean for you, listening? Consider the kinds of new questions we could ask.
The new scenarios we could explore, the insights we might gain. When this kind of high-fidelity, comprehensive climate data isn't just stored away passively somewhere.
But can be actively generated, adapted, right at our fingertips. What does that level of accessibility and dynamism mean for understanding our climate and maybe for taking action?